Hello everyone. In this video, I will derive the final expression of Maxwell-Boltzmann distribution law, which actually gives us the probability of finding a particle in a particular energy level in a given system. In order to start with the derivation, you can look that I had written this expression which I had derived in my previous video, which is actually in which I had actually found this expression by distributing the various particles in a given system into different energy levels. If you had not watched this video, I will post the link in the description box. You can check it out from there. So in order to proceed ahead, I will take this expression as my base and then I am proceeding ahead. So if we take a logarithm of this expression on both the side, we will get ln of, this is called Maxwell-Boltzmann representative factor. So this will be equals to ln of n factorial. Then whenever we take a logarithm, this multiplication summation gets converted into only summation, that is this expression. I will write it as plus, because in multiplication ln m into n gets converted to ln m plus n. So this will convert into this summation sign, and it will be like summation of ln gi raised to the power ni minus ln of ni factorial. So proceeding ahead, I will just rearrange this expression one more time. Ln of Maxwell-Boltzmann representative factor is equals to ln of n factorial plus summation of this. We know that this ni will come in front of this ln, so ln of gi minus ln of ni factorial. So now here if we take a look that here this is ln of n factorial form, and here also we are getting something ln of ni factorial form. And I had already made a video on Stirlings approximation in which I had shown you how for a large number of particles in a system, because here the this capital N or this Ni is very large. So for this particular system where the values of N are very large, we can take an approximation also known as Stirlings approximation. I had also made a video on this, so if you want, I had posted it in the description box. You can check it out from there. So proceeding ahead, if applying the various the Stirlings approximation, we will get, and let me tell you by the way what is Stirlings approximation. So if there is something like ln of x factorial, we can take it like x of ln of x minus x. So this is the Stirlings approximation. We are going to apply it over here. So ln of n factorial plus summation, here if I will apply the approximation in the next line, so ln of ln I gi minus n of ln ni, and this minus will make that minus plus, so this will be ni. Now proceeding ahead, if we take a look at ln of this summation equals to n times ln of n minus n plus, here if we take a look that this summation of this ni will be simply the summation of all the particles in the system, and that will be simply equals to capital N only. So if we take it out of the expression like this, ln of ni plus the rest summation part, for the time being I am representing it by a, the rest part which is being here. So this thing which is the summation of ni, where I is varying from 1 to n, it will be equals to capital N only, and this n and this n will get cancelled out. So finally we can write like this: ln of Maxwell-Boltzmann representative factor is equals to n times ln of n plus summation of the rest particle, the rest thing that I had represented it by A will be like minus of Ni ln of Ni. So this will be the thing that we will be left out after applying this Stirlings approximation. So now, in order to find the Maxwell-Boltzmann distribution law, we need to find the Maxwell-Boltzmann distribution function at the equilibrium, because at equilibrium the particle or the system of the particles will be more stable, and at that time only the number of the particles will be maximum inside it. That is, this quantity, that's Boltzmann representative factor, will be maximum at equilibrium only. So in order to get the equilibrium, or in order to maximize this term, that is Maxwell-Boltzmann representative factor, we need to differentiate our this expression and equate it to 0. Only then we can find the maximum of this Maxwell-Boltzmann representative factor, and that will eventually give us the final expression. So now if we differentiate our equation, this will be like delta of summation of ln representative factor equals to, and yes, this thing n times ln n is a constant, so its differentiation will be a 0. I am not writing it over here. So now it comes our this summation factor. So here only the Ni is varying, whereas Gi is a constant like of thing. So here in differentiation it will not play a role, only we will differentiate with respect to the Ni. So if we differentiate it with respect to the Ni, this will be like d of Ni into ln of Gi, then minus this whole will be d of Ni into ln of Ni, plus it will be Ni times 1 by Ni, because differentiation of ln n is 1 by n. So this will be the final thing we will get, and here this and this will get cancelled out. So here we will left out with only differentiation of Ni. Now one thing that I want to specify over here, that we had already written earlier, that summation of Ni, where I is varying from 1 to n, is capital N. Now if we differentiate this expression, we will get like summation of d of Ni is equals to d of n, that is, which is a constant, it will be 0. So in our expression here we can observe that this summation sign, when will distribute over these two functions, this summation when encountering this d of Ni, it will get a value of 0. So here in the next step I am going to omit this term, because this term after dealing with the summation factor will get 0. So the final expression that we will get will be like equals to some differentiation of the ln of representative factor of Maxwell-Boltzmann is equals to summation of ln of Gi d of Ni minus ln of Ni d of Ni. So this is the final expression that we are getting. Now here we can also make certain certain calculation to make it further more compact. So this will be like summation of ln of this, if we take this d of Ni and d of Ni common from both, we will get ln of Gi minus ln of Ni. So this will be ln of Gi over Ni, and this will be like this. So now one of the important things comes after this, which is there are certain constraints that we need to take into consideration in deriving this expression. That is, the constraints are like summation of I varying from 1 to n, and I is a constant which is called n. Now this we had just written it earlier, this summation from I equals to 1 to n, d of Ni will be 0. Similarly, there is one more thing, that is summation of E of I and I is equals to E, that is the total summation of the energy of all the particles. So this will be also a constant if we differentiate it, I varying from 1 to n, E of I d of Ni will also be 0. So these are the two constraints of these equations, and we need to take into consideration these constraints in order to derive our expression. So let us give our those two constraints a certain constant values. Let us give like alpha times summation of d of ni is equals to 0, where I is varying from 1 to n, and beta times summation where I equals to 1 to n e of I d of ni is equals to 0. These are our two constraint values that we have seen earlier, and in order to incorporate this constraint into our equations, we need to use Lagrangian multiplier, which is quite a deep concept. So I am just here going to apply this thing into our original or the final expression that we have derived after doing certain calculations in our expression. So I'm just going to add these constraints, and adding these constraints into our those equation will ensure that these constraints are taken into consideration while deriving the Lagrangian mechanics, or while deriving the Maxwell-Boltzmann equation. So this is like, I'm going to write, this is like differentiation of ln of this Maxwell-Boltzmann representative factor is equals to summation from I equals to 1 to n ln of, so if I take a minus sign out here, so ln of ni over gi plus alpha times plus beta times ei d of ni is equals to 0. This is our required expression that we wanted to derive, or we wanted to get in order to substitute it with the 0 in order to get our equilibrium condition. So if this expression is equal to 0, this means that this whole thing must be equals to 0. So now equating this in to be equals to 0, we get ln of ni over gi plus alpha times plus beta of ei is equals to 0. Taking this terms into the right hand side, ln of ni over gi is equals to minus times alpha plus beta times ei. So now opening the logarithm, so here we get ni over gi is equals to e times minus of alpha plus beta times ei, and now taking the gi on that side, we get ni is equals to gi times e to the power minus alpha plus beta times ei. So we are quite close to our final expression. This is the thing that we are getting after equating our expression to equals to 0. So here still we are unaware of the values of the alpha and the beta. So if we apply the Lagrangian multipliers, we will get alpha to be equals to minus mu times k times bt, and beta to be equals to 1 by kbt. So substituting these two values in our expression, what we will get is n of I is equals to gi e to the power minus of ei minus mu by kbt. So this is the desired expression that we wanted to derive in this video.